Okay. Good morning, students. My name is K. Razu, Assistant Professor, Department of EEE, SVCE. So today we are going to discuss uh, two-port networks session 2. So in this session, we would like to discuss the image impedance concept and the remaining parameters, two-port network parameters, Y and H and ABCD parameters. Right. In the last class, just recall the information, what we studied, what we learned in the last class. So we have taken the two-port network introduction. So the most common application of two-port networks are found in filters. So that is what just before we discussed. So the most common application of the two-port networks are found in filters or somewhere your transmission lines or to match the different networks. From you can say the telecom antenna systems have two-port identification. So you know very well that so every telecom network having some sending end and receiving end. So there you can find your two-port network application as a port one and port two. So there you can find your application of two-port networks. So these are generally where you are using your two-port network concepts. So I said in your transmission line also we have sending end and receiving end. You know, sending end looks like your port one. You can say that receiving end of your transmission line subjected to port two. So I think you are familiar with the routers. So in our houses we have routers for the purpose of internet connection. So router came a internet cable to as an input, and the router gives so many output cables of your internet. So port one is subjected to your incoming internet cable, and your port two has your output internet cables to your different systems. So this is kind of a two-port network. So while designing this type of antennas and this type of routers, this type of transmission lines, we require the two-port network concept. So if you are able to understand what is going to be happening in the two-port network black box, I think you know familiar about your black box. Black box nothing but the two-port network. Yeah, black box nothing but the two-port network entire structure. So where you can find your two-port network black box nothing but yeah. Let's see your black box. So there we have a input and we have a input. So you can say terminal one, and we have another terminal.
You didn't share the screen, sir.
Yes, yes, is it is visible. Right.
Okay, sir.
Hope you are seeing my screen, right?
Yes, sir.
Yeah. So this is your port two. So you can say in input port you can imagine, and you can granted it is an output port. So this is what your black box. So there itself your entire design aspects are going to be taking place. So here the impedance parameters, your admittance parameters, your H parameters, and your ABCD parameters, and your the filter concepts, whatever. So which is going to be taking as a conversion this input and output. So I just mentioned some of examples for your two-port networks are. So if you look at the router which is there inside of your home, so it is having some uh, input channel and it is having some different output channels. Of course, it is taking some cable as an input, so it will give a different type of routed outputs. So then you can connect to your monitors, different places, your computers at different places. You can connect your different places. You can see this in your laboratories, you can college, your library, so many places. So you can say that input and output. So while the performing this input to different kinds of output, there is a little bit concept which is related to design aspects of this particular router. So if you take an antenna here, So your antenna is subjected to so many different kind of network. So we have some receiving incoming signal and outgoing signal. So you can say that input and output. So there itself your black box here, and there itself your black box. There itself your black box. So these are some kind of applications of your two-port networks where generally in real time we are using. So this is generally used in cellular antennas to transmit and receive coverage signals to specific areas. We told you that specific areas. So, so in our transmission lines also we have an application of this two-port network as an incoming receiving voltage and sending voltage like that. So different kind of aspects. So proceeding to the previous class, in the yesterday's class we have discussed about the impedance parameters of your two-port networks first configuration. So while we're discussing about your impedance parameters, we have two conditions, symmetrical and reciprocity. So based on the conditions, we are examining the two-port network circuit. So while examining this symmetrical network and asymmetrical network, there are some other aspects are going to be came into picture. So I think my PPT is visible to you, right?
Yes, sir.
Yeah, thank you. Let's go for continuation of your previous class. Yeah. So while we're discussing about your two-port network impedance, so we came into know that there is some other concept which is hidden to your impedance parameters or image impedance. So what is meant by image impedance? How you find this image impedance? How this came into picture of your image impedance? So, so basically there are two types of networks. So you know that very well: symmetrical network and asymmetrical network. So a network is symmetrical if its input impedance is equal to its output impedance. So that is what generally we experienced in the last class also. So what is meant by symmetrical? If the symmetrical property is going to be existing here, so we can say Z11 is equal to Z22, right? So you want to say another definition when the electrical properties of the network are unaffected even after interchanging the input and output terminals. So see the definition when, so just when electrical properties nothing but we have different kind of properties. So the properties are characteristic impedance is one of the property, propagation constant is one of the property. So these are the different kinds of properties which are subjected to networks. So when electrical properties, when characteristic impedance or your propagation constant or some other properties, we will come to know that. So when the properties of that network are unaffected, it must be not change even after changing the input and output terminals. So you must change the input and output terminals, then the network properties are not going to be disturbed. Then you can say that that network is called symmetrical network. Very beautiful definition. So what is mean by asymmetrical network? So when electrical properties of that network get affected after interchanging input and output terminals. If you change the input and output terminals, the properties of your electrical properties of your particular network, it may be any kind of network, are going to be changing. Then this type of network is called asymmetrical network. See the depth of your network. So we just came into a simple two-port network. After the two-port network, we came to realize that there is a symmetrical network and asymmetrical network. When you say that it is a symmetrical network, the electrical properties of that particular network unaffected because you are interchanging input and output terminals. So it is the properties are not affected. Then you can say that network is a symmetrical network. So when the electrical properties of that particular network get affected, then you can say that that network is a asymmetrical network. So symmetrical network having some electrical properties and asymmetrical network having some properties. So based on the property changes, you are going to be deciding. So let's see some of the properties of your electrical network. So properties of your networks. Yesterday we got this question from one of the student. Just I'm addressing. So properties of your networks. So we have two kind of properties for symmetrical network: characteristic impedance and propagation constant. So these are the two properties of your symmetrical network. Symmetrical network. So likewise, asymmetrical network also has three properties: and image impedance, iterative impedance, image transfer characteristic constant, image transfer constant. So these are the three properties of your asymmetrical network, and these are the two properties of symmetrical network. So in our academics, we are going to be already dealing with the characteristic impedance and propagation constant, but the unknown factor which is going to be here is really image impedance. So what is mean by image impedance? How it is going to be uh, calculated for the two-port network? How the iterative impedance is going to be calculated for a given two-port network? How image transfer constant is going to be calculated for given two-port network? We will see. So a little bit derivation will takes place. Try to understand what is mean by image impedance. So in order to get this image impedance and iterative impedance, I would like to take some equivalent circuit. That is what I just told you in the last class. By taking some equivalent to T network or phi network, we will are going to derive this image impedance for a particular network. So generally, you know very well that we are using generally T network for the transmission phi network for transmission purposes in generally. So that's why I'm taking some equivalent to T network in order to examine, in order to derive this image impedance, how it is going to be calculated for a given two-port network. So just I'm taking a T network for the better understanding. Okay, let's see. Yes. So today now we are discussing about the asymmetrical network properties. So the asymmetrical network properties are, you know that. So image transfer constant and your image impedance and your iterative impedance. So these are the asymmetrical network electrical properties. If you change the inputs of that network, if these properties are changed, you can say that that network is a asymmetrical network. In this way, you are going to be distinguish uh, symmetrical network and asymmetrical network in a network theory concepts while designing the filters. Right. So now we will discuss image impedance. So the first property of your asymmetrical network. So this is symmetrical network, and we have the properties. First one is image impedance. So image impedance, how it is going to be dealing with in a T network. Just I have a T network. Okay, so just don't think that it is a resistor, just an element. So it is having some Z1. So obviously this is subjected to port 1. This is subjected to port 1. In general, we are taking this is subjected to port 2. So what is the name of this impedance? Generally, my dear students, the name of this impedance which is there located here, we generally name it as Z2 or Z3. So we are name it as obviously Z2 because it is a port 2 and Z2, port 1, Z1. So similarly, we are following, most of the authors are following it like this. There is no specific reason. So we have just a port 1, Z1, port 2, Z2, and this port 1 to port 2, we have Z, not issue. Plus a minus V1, and we have port 2 plus minus, and we have port 2 current I2, and we have port 1 current I1. This is a simple equivalent of T network. For a symmetrical network, we are considering now. Now, if I consider a load at port 2, so just try to understand. If I consider a load at port 2, name as ZI2, ZI2. Just I was consider a load at port 2. So try to catch this point. Try to catch this point. If I consider a load at port 2, if I consider a load at port 2, so try to notice this point. If I consider a load, if I consider a load at port 2, the load name is ZI2. You can say that image I stands for image, Z for impedance of two networks. Just I am considering at port 2 a load called the image impedance ZI2. So just I'm connected a load in such a way that ZI2 to port 2. So then if you look at port 1, if you look from port 1, if you look from port 1, what you generally observe is Z image I1. So try to understand. So if I connected a load at port 2 that is named as ZI2 and it is found a value ZI1 at port 1, ZI1 is called image impedance of that network. Image impedance of that network. So when I was connected a load at port 2 ZI2, so there is some kind of value which is going to be taking place at port 1 when you look from port 1. So when you look at from port 1, so there is some finding of ZI1 which is subjected to this load. So ZI1 is called the image impedance. So this is one circuit which is going to be taking out into consideration in order to find ZI, what is the value of ZI1. So just a similar way, in a similar way, in a similar way, if I consider, if I consider, if I consider another load, if I consider another load at port 1, the name of the load is ZI1. So if you look from port 2, if you look from port 2, what we generally observe is image impedance of port 2, that is ZI2, is going to be calculated. So what is the value of ZI2? So what you need to be understand here is if I load is port 1, that is ZI1, if a load is at the port 1, ZI1, now the image impedance is ZI2. If we connect ZI1 as load, we will get ZI2. So when you are getting ZI2 means when you connect a load ZI1 to this particular network at port 1, then you will realize the image impedance of this entire circuit is ZI2. If I connect a load here, ZI2 as a load, so then I was calculating image impedance as ZI1 for this entire network. So how to find the image impedance of that particular networks, we will see now. So how to calculate image impedance. So image impedance nothing but when we have a load at port 2, by taking the name of that load is some ZI2. For the mathematical purpose, I'm taking ZI2. So you are calculating a image impedance of that entire two-port network is named as ZI1. So in a similar manner, we have a load at port 1. You can name it as ZI2. Then if you look at port 1, you need to be calculate ZI2 from port 2. So these are the two values you need to be finding out in order to differentiate, in order to determine your image impedance of that particular asymmetrical network, like two-port network, asymmetrical network of two-port network, you can say. So we will derive the image impedance of that two-port network now. To match the impedances for different networks, this kind of image impedance concept is going to be useful very well in practical. So to match the different networks, to connect the different networks. we require the image impedance concept. So try to be take one simple circuit. I'm not deriving the entire derivation part. So just I'm giving some brief idea how to be calculate image impedance of a particular network. So just I was connected a load here. The name of load is Zi2, and you are looking from port 1, so you will get Zi1. So already you know that values Z1, Z2 and Z3. So now you are calculating the image impedance of that particular network. Just go through this one. Zi1 is equal to Zi1 is equal to yes Z1 plus these two are in series again with this parallel, right? So we can say that Z3 in parallel with Z3 is in parallel with
Z2.
Z2 plus Zi2. This is the image impedance of your network. So then after finding different values of this one, so we can say that you have got some value. So you got Zi2 here and you have Zi1 here. After some manipulations here, Zi1, Zi2 plus Zi1 of Z2 plus Z3 minus, it just came into this type Zi2 Z1 plus Z3 minus of Z1 Z2, we have a product with this minus of Z2 Z3 minus Z1 Z3. So all this together we can write minus of summation Z1 Z2 we can write. So this is equation number 1. You can say that Zi1 Zi2 plus Zi1 is common and Z2 plus Z3 minus Zi2 Z1 plus Z3 of minus Z1 Z2. This is, you can say that equation number 1. So just remember this equation number 1 is subjected to when load is connected. When the load is connected at port 2, the name of that load is Zi2. When you look from port 1, you will find an image impedance of this load Zi2 is Zi1. So how to calculate Zi1 means we got some equation number 1. Equation number 1. So just similar way, if you go for your load at port 1. So just we have load here. The name of that load is Zi1. So if you look from your port 2, you got image impedance Zi2. So Zi2 value is going to be find out in such a way that Zi2, so just a similar equation, Zi2 is equal to from here. So Z1 plus Zi1 is in parallel with Z3. Hope you understand. So Z2 plus the combination of this parallel Z3 in parallel with Z1 plus Zi1. Yeah. And then we got another equation in a similar manner, which is subject to previous one. So Zi1, Zi2, after multiplying these two and by taking the uh, conversion from this side, you got Zi1, Zi2 plus Zi2 Z1 plus Z3 minus Zi1 Z2 plus Z3 minus summation Z1 Z2 Z2 Z3 minus of Z1 Z3. So it's in a simple manner, summation Z1 Z2 we can write that is equal to 0. So all this get this side is equal to 0. This is equation number 2. So now we are calculating the image impedance of that particular network. How you are going to be finding out that image impedance? That is the concept what we are discussing for a two-port network. In that a T network, how you are calculating the image impedance. So what is the formula for image impedance? How you are going to be obtaining that image impedance? So there is no direct formula you need to by heart. So we have some little bit concept how it is going to be derived. So that is what we are seeing now. So we have equation 1 and equation 2. So by using these two equations, we are going to be getting out our result. We are going to be getting out our result. So let's look. So I hope you have two equations. So from the two equations, if you go for 1 minus 2, if you go for 1 minus 2, so then you can having some subtractions. After the subtractions, you can find that Zi1 divided by Zi2 is equal to Z1 plus Z3 divided by Z2 plus Z3. So this is very important relation for our next procedure. So if you take out 1 minus 2, equation 1 minus 2, equation 1 minus equation 2, if you perform that above two equations, then you will realize Zi1 by Zi2 is equal to Z1 plus Z3 by Z2 plus Z3. So you can say equation number 3. And if you perform equation 1 plus 2, so that is why yesterday it is not sufficient time to discuss this image impedance concept. So if you perform equation 1 plus 2, then you can get an expression Zi1, Zi2 is equal to Z1, Z2 plus Z2, Z3 plus Z1, Z3. So after adding these two equations, already we got equation 1 for your T network when load is connected at port 2. We got equation 2 when load is connected at port 1. After adding these two equations, you will get this one. You can say in a simple manner, Zi1, Zi2 is equal to summation Z1, Z2. If you remove this summation, you can say about this one. So then you just mention this equation as equation 4. Equation 4. This is equation 4. So we got equation 3 and equation 4 from 1 and 2. From 1 and 2. So just another concept we need to be taking out in order to find the image impedance. So far we didn't find the image impedance. So just perform equation 3 into equation 4. So equation 3 into equation 4. So what is equation 3? Zi1 divided by Zi2 into Zi1 Zi2 is equal to this one, is equal to Z1 plus Z3 divided by Z2 plus Z3 into summation of this one, summation of Z1 Z2. So just Zi2 getting cancel out, Zi2 Z2 cancel out. You can say that just I am removing this one. Equation 3 and 4 we are multiplying in order to find our image impedance. So still we are approaching. So Zi1 square is equal to Zi1 square is equal to, we got Z1 plus Z3 divided by Z2 plus Z3 into your summation of Z1 Z2. So you got finally Zi1 is equal to root of Z1 plus Z3 divided by Z2 plus Z3 into summation Z1 Z2. Sir, where we have values for Z1 Z3 in your given network. So find the image impedance of a two-port network at port 1. So just go for this formula and substitute the values, you will get the result. So very, very important image impedance concept. So little bit awareness required. So Zi1 is equal to Z1 plus Z3 divided by Z2 plus Z3 into summation value. So just to go for next step of your image impedance concept. Just to hope you have this value with you right now. So just I'm performing equation 3 divided by 4. Yes, go for this one. Equation 3 divided by 4. Equation 3 divided by 4. Equation 3 divided by 4. If you perform this equation 3 divided by 4, what you get? Zi1, Zi2 divided by Zi1 divided by Zi2, that is equal to, so it is going to be reverse, right? Z1 Z2 into Z2 plus Z3 divided by Z1 plus Z3. So here Zi1 getting cancelled out. If it is go above side, so we got Zi2 whole square is equal to, so your Z2 plus Z3 divided by Z1 plus Z3 into your summation value, obviously Z1 Z2. So if you remove Zi2 square, sorry, so if you remove the square, then obviously Zi I2 is equal to root of that value. Z2 plus Z3 divided by Z1 plus Z3 summation Z1 Z2. Very important relations you need to be catch. So while we get the question in the gate examination, find the image impedance of the two-port network at port 2 when a load is connected at port 1. So then you have to go for this one. So just you can extract this one, obviously Z1 into Z2 plus Z2 Z3 plus Z1 Z3. Hope you know this one. So in this way, you are finding out the image impedance of your particular networks, particular T network. So we have another concept which is going to be taking place with the image impedance concept is off network image concept. Off network image impedance. Find the off impedance image network. How you are going to be calculate? See, the beauty of this image impedance concept is off off image impedance. We will check out what is meant by off image impedance. Hope you have this equation with your notebooks. So just going for off image impedance concept, how it is going to be calculated for a network. It is another diversion of your image impedance concept. We have a chance to get this type of different questions. Image impedance, off image impedance. I have a network. So, so obviously we are generally assigning that Z1 and Z2 and Z3 here. So what is the off impedance of image impedance of this network of network? So if they want off image impedance of this one, So if you want to calculate ZI1, so you want to calculate ZI1, put Z2 is equal to 0. Why? Because they are requiring the image impedance for the off network only, off network only. So this just neglected. Put Z2 is equal to 0 in above your ZI1 equation, then you will find ZI1, ZI1. So if you want to calculate ZI2, so ZI2 nothing but it is subjected to port 2, right? And that is mean the examiner asking you the question at port 2 ZI2. So substitute ZI1, sorry, substitute, substitute Z1 is equal to 0, then you will get Z2, ZI2. So in this way, you have to analyze the network in a image impedance concept manner. So how to we find of image impedance concept, how to find image impedance of a network. So these are the very important aspects you need to be concentrate. Let's see. So we have another property which is going to be very important, that is iterative impedance for asymmetrical network. Iterative impedance of asymmetrical network. Iterative impedance of asymmetrical network. I will give you some brief idea how to find iterative impedance of asymmetrical network. This is another property of your asymmetrical network. See, when the input and output are going to be affected because of the change of input, then this type of properties came into picture in your networks generally. That's why we are concentrating on a symmetrical network. Why? Because you want to get in a symmetrical pure manner, the system is going to be always subjected to the disturbances. That's why the asymmetry of the network is going to be taking place always. That's why these all came into picture generally. So next is iterative impedance. Iterative impedance of your network. So, so already you know that when you say that asymmetric network, so input and output value change, the properties are going to be changing. So generally, when you look at input, what are the circuit parameters you are going to be visible? Z1 and Z3. So if you look from port 2, what are the generally visible values? Z2 and Z3. So already we discussed this point. Based on this one, we are going to be calculating iterative impedance. Z1 here, Z3 here, Z2 here. So when you look from input, so what are the parameters of what are the values of your network are going to be visible Z1 and Z3. So when you look from your port 2, what are the generally visible values are going to be appearing Z2 and Z3. So that is nothing but when you look from your uh, port 1, sorry, port 1, the visible values are Z1, Z3. So when you look from port 2, the visible values are Z2, Z3. So see, only Z3 is common, but this is going to be changed. So the parameters are not going to be same from port 1 to port 2. So you just imagine the network is going to be calculate the iterative impedance. So now we are calculating the iterative impedance of a particular network. So we'll take out the screen. So take an asymmetrical network. So just I am assuming an asymmetrical network here. So I have an asymmetrical network here. Z1, Z2, Z3. Consider a load at port 2. So this is the difference. Try to be concentrate, understand this point. Consider a load here. The name of that load is ZT1. T stands for iterative and Z for impedance, iterative impedance. So load name is ZT1. So calculate the iterative impedance of this network ZT1 from port 1. See the difference from your image impedance to your iterative impedance. I have a network, I have an asymmetrical network here. I have an asymmetrical network in Z1, Z2, Z3. So connect a load, add this port 1. The name of this load is Z2T2, and you need to find iterative impedance of this network Z22 from port 2. Z22 here, Z22 here, ZT1 here, ZT1 here. So iterative impedance equivalent circuit of a T network, of a T network. So if you look at these two circuits, so you are going to be calculating the iterative impedance of your network. Just a simple procedure. So I have ZT1 is equal to, for circuit 1, ZT1 is equal to, yes, anybody? Z1 plus Z3 is in parallel with Z2 plus ZT1, right? So this is the combination of this network. So these are in parallel again in series to this Z1. So if you manipulate this one, you will get ZT1 square. Here also T1 is there. ZT1 square plus ZT1 of Z2 minus Z1 minus Z1, Z2, Z3 is the summation Z1, Z2 is equal to 0. So look at this equation. It seems to be second order equation. So ax square plus bx plus c is equal to 0. So where A is equal to your ZT1, B is equal to, sorry, A is equal to your 1 and your X is going to be ZT1. Your A is going to be 1 and your B is going to be Z2 minus Z1 and your C is going to be summation Z1, Z2. So this is a second order quadratic equation. The roots of this equation, you know that the roots of second order quadratic equation. So you are calculating the iterative impedance of a network in the examination if you get a question. So ZT1 is equal to minus B plus or minus B square minus 4AC divided by 2A, right? So minus B minus of Z2 minus Z1 plus or minus root of Z2 minus Z1 minus B plus minus B plus or minus root of B square. So square, no, square minus 4 A value 1 and C is going to be summation Z1 Z2 divided by 2 A value is going to be 1. This is the root of that second order equation. So you need to find ZT1. So if you go for this simplification, ZT1 is equal to ZT1 is equal to, you can say, I can say that Z1 Z2 divided by 2. Yes, obviously Z1 minus Z2 divided by 2 plus or minus. So just here 4 is there. So 4 is going to be getting cancelled out, taking common from this root. Then you will get 2. So then in the root, uh, z2 minus z1 whole square divided by 4. 4 is going to be getting cancelled out and we will get root, right? So plus, so minus 4 is there. So you got c value is minus 1. That's why you got plus here. So plus summation z1 z2 divided by 2. Hope you understand. Our c value is minus summation z1 z2 c value. So that's why 4 ac c value minus minus into minus plus. So if I close 4 1 into z1 z2. So 2 getting cancelled out. The remaining answer is the iterative impedance of your network is zt1 is equal to z1 minus z2 divided by 2 plus or minus, we can say that root of z2 minus z1 divided by 4. This is square summation z1 z2. So similar way you can find for network T2 also. Z T2 is equal to just the similar way representation of or changing of values. So Z2 minus Z1 here by 2. So I can write the similar way of your equation by seeing this one with another color. Z T2 is equal to Z2 minus Z1 divided by 2 plus or minus root of Z1 minus Z2 divided by 4. This is square plus summation Z1 Z2. These are very important equations in order to find the iterative impedance of your network, of your two networks. So you want to calculate of nothing but you just make sure Z2 is equal to 0 from you are calculating ZT1. So if you want to calculate ZT1, again Z2 is going to be 0, then you can find ZT1. So these are the very two important equations in order to find. So generally, so for finding of network, that is, so generally we are approaching, so we have plus or minus, right? So generally we are taking the network is positive impedance, we are taking always. So that is, so this is the iterative impedance and your image impedance problems while we discussing as a question in the gate examination point. So coming to our class, so we are focusing on Z parameters and followed by your image impedance and iterative impedance of your asymmetrical networks and this its calculations. Move on to the next two-port network parameter, that is Y parameters. Okay, students, we'll proceed now.
Yes, sir.
Yeah, look at these two-port network of Y category. So we have the two-port network Y parameter equations. I1 is equal to Y11 V1 plus Y12 V2. I2 is equal to Y21 V1 plus Y22 V2. So in a matrix form, we got the Y parameters Y11, Y12, Y21, Y22. So just take a little bit impedance circuit in order to find these Y parameters. In the examination, I think so one of the previous question paper also, question also I have given here. So just go for the previous question, how to get the answer for your Y parameters when impedance are going to be involved in the two-port network. Y parameter calculations. Just I'm zooming the circuit. Right. So compute the Y parameters of the given network. I have taken all the parameters, but in the examination, they are asking for only Y21. But time being, if you practice all these parameters, you have some good knowledge. So I'm just taking a two-port network is given, and we have a capacitor here, and we have an inductor here. Compute y21. This is the question asking. So I have a values in such a way that C here, L here, and they mention 1 ohm here. So obviously V1 plus minus I1 here. So this is simple circuit they given, and you need to find Y21. So generally, Y parameters is called short circuit parameters or admittance parameters. The name itself, it is giving information that. So by short circuiting the circuit, we are going to be calculating the Y parameters. So if you go for the procedure to calculate these Y parameters, so generally we are following short circuit method here to solve Y parameters. Case 2 or case 1. So port 2 short circuited. So short circuit nothing but current is going to be available, but voltage is going to be zero. So no need to mention current. So obviously it is there in the short circuit. So voltage is going to be zero. Which voltage? P2 voltage, right? Because it is subjected to port 2. And the circuit is redrawn. The circuit is redrawn. We have a capacitor. We have a resistor here. So we know that from the fundamentals, when you short a circuit here, all the current which is coming from port 1 is entirely going for short circuit only. Why? Because current always chooses the less resistance path. But here we have an inductor. That's why all the current is going to be subjected to this short circuited part. That's why there is no current is going to be happening in the inductor. That's why that inductor value is neglected, and we are short circuiting the port 2. And we have capacitor, and we have 1 ohm resistor here, and we have V1, and we have a current I1. Just go for very simple problem. So how to be taking out the C value? So C is subjected to 1 by S, and L is going to be subjected to S. So here it is C 1 by S. So in order to find for the two-port network parameters, what you get after short circuiting port 2, V2 is equal to 0. Yes, I1 is equal to Y11, I1 we have, and I2 is equal to Y21 we have, so V1 we have. I1 is equal to Y11 V1 we have, I2 is equal to Y21 V1 we have. Just to go for the procedure, how to find a simple manner. No need to go for maps and nodal, all these things. Just we are calculating a simple manner for finding Y11. So you are going to be calculating Y11. Y11. So in order to find Z11, Z22, Y11, Y22, we are approaching or equivalent method. So if it is a L and C values combination, Z equivalent method. Just go for this Z equivalent of this network. Z equivalent of this network. See, current is going to be here. After reaching this point, current is going to be divided into two parts. That's why this one and this one are going to be in parallel. You can say that one bias is in parallel with
1 ohm.
1 ohm. Sorry, in the examination, I think we got the value of your resistor is 2. So just 2. Sorry, 2. 2 value. So you will get 1 by s in parallel with s2. Then you can say that it is 2 into 1 by s divided by 2 plus 1 by s. So the result is you got 2 ys divided by 2 plus 1 by s. 2 plus 1 by s. This is R equal. Just apply your voltage at your port 1. Then you can easily grasp this point. V1 is equal to I1 into Z equivalent. Why? Because this network contains inductor and capacitor. That's why I'm taking Z equivalent, not R equivalent. So our target is here Y11. In order to get Y11, what is that? y11 is equal to I1 by V1. So just make sure I1 by V1 is equal to 1 by Z equivalent, right? 1 by Z equivalent nothing but this value, right? So you can say that 2 plus 1 by S divided by 2 by S. So if you simplify this one in a simple manner, 2S plus 1 divided by S is there, S is getting cancelled out. You will get 2 here. And in a simple manner again, 2 by S by 2, 2 to getting cancelled out, yes, plus 1 by 2 means 0.5. So this is I1 by V1, that is equal to Y11. 1 is there, 1 is there, 1, 1. Of course, it is an admittance. Admittance formula is ratio between current to voltage. I by V, I1 by V1, Y11. Admittance units are mho or semi. Yes, yes, plus 0.5. See how simple it is without going for different conversions at all those things, right? You got y1 mama. Next we will go for next parameter which is there. What is the next parameter we get from our circuit?
Y21.
Y21. Just move on to the Y21. Very simple. If it is an AC circuit contains your inductor capacitors, no issue that. So just stick to your method, whatever you learn. It may be node or it may be mesh. Not an issue in order to solve the two-port networks. So the perfection is very important to get your exact answer. That's it. So if you practice thoroughly, then you will get your solution without any hesitation. So now your target is find Y21. So in order to find y21, we have I2 divided by V1 we want to get. So if you get this I2 by V1, you will get y21, obviously. So in order to find this one from our circuit, look at the circuit. Look at the circuit. We need I2 value. Though we have in port to short circuited, I2 will be present. Yes, I2 will be there. V2 will be 0,
Yes, sir.
but I2 will be there. So we can write from this one V1 is equal to V1 is equal to the applied voltage at port 1 is equal to, so this is the branch in parallel with this V1, in parallel to this V1. So same voltage here and here is same, and here also same voltage. So we can write V1 is equal to 2 I2. See clearly, this branch and this branch are in parallel to this V1. So same voltage here across this capacitor is V1, and the same voltage across this resistor is also same, 2 ohm here. Same. Then we can write V1 is equal to 2I2. But of course, the current which is there in port 2, I2, is coming opposite to your current I1. That's why we are making this is minus. Very important. You need to be just check out this one. Minus 2 I2. Why we have taken minus here? The current direction is opposite to your I1 current. That's why minus 2 I2. So from this, our target is admittance. Admittance nothing but ratio between current to voltage. I2 by V1 is equal to I2 by V1 is equal to what?
-2. -1/2.
Minus 1 by 2. Current to the voltage admittance. You can say more or yes. So the value is minus
Y21 equals to -0.5.
0.5. Very simple. In a simple, without any doing any manipulations and calculations and applying. So you are getting. But the most probably, generally the students are mistaking here, minus taking the value to opposite of your current. That is very important. Try to be concentrate here. V1 is equal to minus 2 I2. Okay. So we are going for next two parameters of your given network. So hope you understand thoroughly how you are going to be taking out the network in order to solve Y parameters network in a simple manner. But there is no problem to apply mesh and nodal analysis. You can approach that method also. So that is also well and good method, but it's taking some 1 minute time to calculation for the calculation. Just going forward, case 2. So port 1 again short circuited. Why? Because Y parameters are called short circuit parameters. Port 1 short circuited. So in the short circuit, voltage is going to be 0 V1, and your current will be present. Current will be present. Y1 current will be present. Then your network is going to be so if you short circuit here across the short circuit, the remaining elements are going to be neglected. Then you have your resistor here, and clearly your inductor here, and of course there is a short circuit. So we have voltage plus minus. So we have a current I2 here. Obviously, current I1 is also present here. So this is 2 ohm, and this your inductor L. You can say name it as S. So simply, our parameter equations, what we have is now in our hand is I1 is equal to Y21, V2 we have, and I2 is equal to
Y one to
Y22,
V2, sir.
Y, sorry, we have Y12 V2, and I2 is equal to Y22 V2 we have. These are the two available equations with us. So actually our target is Y12. So that is what generally asked the question, and we are making all the things. So by looking after these two equations, generally we are approaching Y22 first. So by taking Z equivalent method, so if you find Z equivalent of this network, Z equivalent is equal to, just look after from here. Yes, in parallel with these two. Yes, in parallel with these two. So 2s divided by s plus 2. That is equivalent resistance, equivalent admittance, sorry, equivalent impedance from you get. So we can write our equation. V2 is equal to I2 into Z equivalent of that entire network, entire circuit. So our target is I2 by V2, ratio between current to the voltage. We can name it as Z22. That is equal to, just make sure, 1 by Z equivalent, 1 by Z equivalent. So if it is 1 by Z equivalent, that is equal to S plus 2 divided by S plus 2 divided by 2S. So if you want in a simple manner, so SS getting cancelled, 1 by 2, 0.5 plus 2 by 2 by S, you can say 1 by S. Is more or Siemens, 0.5 plus 1 by S. So in our options, we got 2 plus 1 by S, 2 plus 1 by S, 0.5 divided by 1 by 2s, 0.5 by 1 by 3s. Like that, the different answers will be appear in the examination. So try to be look after your answer where it is available. So another parameter we need to find is y12. This is also very simple. Just go for this one. Again, another color. So y12 right. So in order to find y12, just approach y12 is there. So I1 divided by V2. So we require these values. So just go for this V2. V2 is equal to, VT is equal to, how can we write? So the same voltage here and the same voltage here. So what is the voltage in this branch?
2I1.
Yes, minus 2I1. So the current is opposite to your I2 current. So to this port 2, that's why V2 is equal to minus 2 I1. So then we can, I1 by V2 is equal to minus 1 by 2 is equal to minus 0.5. Sorry, more. Yes. So in this way, we can calculate the parameters of your network easily. So hope you understand how to calculate the Y parameters for a given network in a simple manner by using these current divisions and your two-port network equations itself. So no need to, we are not approaching any kind of mesh and nodal analysis here to solve your questions. So for the sake of simplicity, the width method you can approach easily. That is sufficient method. That is a suitable method. So no need to follow this method for a particular student. So the understanding levels is going to be different for each and everyone. So some of the students are very comfort with mesh analysis. You can easily crack by using your mesh analysis to these equations. Okay, I will give you some question for today's class. Uh, for H parameters also, very simple method. So in this way, we can calculate the parameters for a given network in a simple manner. So just go for your H parameters. So let's recall the information. Short circuit and admittance parameters or Y parameters are having the currents I1, I2. So you are calculating in such a way that Y11 is called driving point admittance and Y12 is called reverse transfer admittance. Try to be concentrate on your question. If he mentioned reverse transfer admittance, find the reverse transfer admittance of the given network. You need to be realize that it is Y12. And the third one, forward transfer admittance Y21. So output driving point admittance Y22. So these are the admittance parameters what we calculated so far. And the conditions for reciprocity of your Y parameter network is Y12 is equal to Y21. I think so. In the given problem, we achieved this
So,
reciprocity
definitely.
condition. Yes, of course, but the symmetry is not satisfied. I think so, right?
Yes,
Yeah,
sir.
yes. Then you can realize that that is an asymmetrical network. That asymmetrical network having the properties of your image impedance and your iterative impedance and your transfer impedance constant. So these are the different properties which are subjected to asymmetrical network. Of course, it is satisfying the reciprocity condition, but not satisfying the symmetry. So looking after your Y parameter network, we have taken this problem. Look after this A, B, C, D, and H parameters. Very simple manner we can achieve these two. So just look after this H parameters. H parameters are given by the two equations, fundamental equations. V1 is equal to, so V1 is equal to H11 I1 plus H12 V2. I2 is equal to H21 I1 plus H22 V2. So in a matrix manner, we got the H parameters H11, H12, H21, H22 into I1, I2. So these are the H parameter equations. Just take a problem with respect to these H parameters. For the same network also, we are going to be calculate ABCD parameters. So I have a gate 2011, I think so. This is one of the question they are asking in the examination. I think they mentioned all the parameters as an answer, ABCD. You need to find all H parameters for this question. Find the H parameters of the given network. That is a question asking. So in options, they mentioned all values. So I have here 10 ohm. I have here 20 ohm and plus minus. Here plus minus they mentioned and they mentioned here current is I2. They mentioned current is I1 here. And we have I1 and this is V2. This is a given circuit they given in the examination. So H parameter equations are given by anybody. So V1 is equal to H11 I1 plus H12 V2. The name itself it is in a hybrid. So you will get short circuit as well as open circuit values here. I2 is equal to change the color. I2 is equal to H21 I1 plus H22 V2. So V1 is equal to and I2 is equal to, these are the two fundamental equations of your two-port network. Just look after. So I said it is in a hybrid parameters. So in port 2, you want to get the parameters, V2 must be equal to 0, and your port 1, you want to get another parameters from port 1, you must be I1 equal to 0. Then only you will get the 4H parameters. The main voltage nothing but is in a short circuit and current must be in an open circuit. Then only we can achieve that two values are going to be equal to 0. That means we have hybrid combination. We have one voltage and current combination here. So just go for case 1 here. Case 1. So just go for port 2. So port 2, what is the parameters which is there in the equations? V2. So port 2, V2 is equal, that in port 2 short circuited. If you short the port 2, what is going to be the value which is going to be happening in the circuit is, so we have 10 ohms here, and we are short circuiting the port 2, and across the short circuit we have 20 ohm resistor that is going to be eliminated. Why? Because across the short circuit, if it is any parallel branch, that is not having any impact. So plus minus, we have I1 here. See how much simple it is. But of course current will be available here, I2 here, but V2 is going to be 0. So we have our equations here. V1 is equal to H11 I1. uh,
I2 equals
I2
to
is equal to
H21,
H21
H21
I1. Yes, thank you. Very good. So I2 is equal to H21 I1. Just to calculate H11. So we want our equations in such a way that V1. So we can write V1 is equal to, so nothing is not there,
and I1.
10 I1, right? Very good. So we got V1 is there, we got I1 is there. So we can make sure that V1 by I1 is equal to 1 is there. H11 is equal to V1 by I1 is equal to here. You just look after this. V1 by I1 is equal to H11, that is 10. V by I, that is 4. Okay. It's a very simple. V1 by I1 is equal to H11, that is equal to 10 ohm. So this our next parameter is H21. Just go for that H21. So we are going to calculate H21. So H21 is going to be available here. We must be get I2 and I1. So then only we can achieve this H21. So from the circuit, from the modified circuit, what we can write, I2 is equal to,
Minus I1.
is absolutely minus I1. So the current which is going to be happening opposite to your current. So I2 is equal to minus I1. We can say that I2 is equal to minus I1. So look after your equation how it is going to be there. I2 is equal to H21 I1. So then we can write I2 by I1 we required. So then I2 by I1 is equal to, so we can say minus here, no problem. Minus 1. I by I, amperes by amperes getting cancelled, unitless. Minus 1 is the answer. That is equal to H H 2 1. 2 is there, 1 is there. 2 1. Very simple, very simple. In a single step we are getting, by seeing the circuit itself we can write H21 is equal to minus 1. That much of simple. So just go for your next two parameters of your network. So in order to achieve your next two H parameters, what must be the necessity arrangement you must be done in the circuit, in the given circuit?
Open circuit port 1, sir.
Port 1. So then we can open circuit this port 1. So if you open a circuit across, then what is the values which are there in series to this open circuit, that is are going to be eliminated. So your 10 ohm resistor is in series to your port 1, then 10 ohm resistor is not going to be considered. Why? Because there is no current flowing in 10 ohm resistor. That value is not going to be considered. It's a negligible value. So just you are opening your port 1. So you can say case 2, port 1 open. In open circuit, current I1 is going to be current I1 is going to be 0, but voltage will be present. V1 will be present. So your circuit is going to be modified like this. And we have V1 plus minus, and of course, your current is going to be 0 here. I1 is equal to 0 here. So then we have V2 here plus minus, and we have current I2 here. So we have 20 ohm resistor here. So what are the equations we will be getting because of this port 1 open? We get the V1 is equal to H
H1 to V2.
H1 to V2, and we got I2 is equal to, I think it is H2 to V2. These are
Yes,
the
sir.
two equations will be available because of this port 1 open. So from this we can easily trace out our remaining parameters. So generally we are following a method in such a way that find H22 first. So in order to find H22 here, look after this, I2 is there, V2 is there. I2 is there, V2 is there. Just apply V2 is equal to, so V2 will be there at port 2, V2 is equal to,
20 I2.
yes. So same 20 ohm resistor is across your V2, then we can write 20 into I2. So our H22 is going to be getting out I2 by V2. So then I2 by V2 is equal to 1 by 20. 1 by 20, that value is, I think it is 0.05. So I by V, it is an admittance. The unit of this one is mho or s. Same. That much of simple. H22 is over. Then again we need to find H12. So in order to find H12, so we must be get our equations V1 and V2 in terms of V1 and V2. So just apply V1 here. V1 is equal to V1 is equal to 20
20
I2. I2,
I2.
oh, I2 only the current which is flowing in the present circuit. Why? Because I1 is already 0. That's why only I2 current will be available in the circuit. So V1 is equal to 20 I2. So how you are going to be removing these? Uh, so you required the value V1 and V2 only, but here our current is going to be available. So we need to remove this I2 value. So we can write V1 is equal to 20 into, just replace this value
V2
here.
by 20.
Yes. V2 by 20 we can write. So 20 getting cancelled out, we will get V1 is equal to V2. So our required is in order to find H12, V1 by V2. V1 by V2 is equal to 1. That is equal to H12. So voltage divided by voltage, units getting cancelled out, no units. So H12 is equal to 1. So in this way, you are framing your H parameter equations by seeing your four options of your network. You can select any appropriate answer which is there where your answer. Just to find the ABCD parameters also for this network, which is going to be available on the screen. So 10 and 20 ohm, just ABCD parameters are going to be just like, so V1 is equal to AV2 minus B I2, and I1 is equal to I1 is equal to CV2 minus DI2. So if you put this one into matrix form, V1, I1, so ABCD, V2 minus I2. So just little bit concentrate is required here, minus I2 will be there. Not simply it is plus I2, it is minus I2. So, so you want to be remove here minus. If you want to take plus I2, then minus B you need to be take out. Minus D you need to be take out. So this is very simple. ABCD parameters. So these are the generally asking questions in the gate examination point of view for our purpose. I think so. This question we solve the H parameters of the given network zone 2010. So just take out your approximate answer. So we can solve this type of questions by using this mesh and nodal analysis and your mesh equations also. But just we are taking this circuit by using simple conversions like voltage to current conversions. So the interconnection of two port networks also are having some important for competitive examinations. Try to be have a look how the networks are going to be connected in a interconnection manner. So if the two networks are connected in parallel, we can say YA YB here. So you want to add these two parameter networks. Y is equal to YA plus YB. Why? Because they are admittance. So in parallel, this is the formula you need to be note it down. Again, series connection of two impedance, two port networks, ZA, ZB. This is another circuit, this is another circuit. So you are interconnected these two networks. So the combination of impedance, total value of impedance is Z is equal to ZA plus ZB. So the cascade connection of two networks, TATB. So you can multiply the TATB directly here, TA into TB. So when the network is like cascaded. So series connection, parallel connection, and cascade connection. So most probably they will take most time when the two networks are given as a parallel and series and cascade connections in the examination. So most probably you will get a question directly a simple plain network which is having inductance, capacitance, and resistors, and voltage sources and current sources generally. So these are the very important concepts you need to be get in the examination of your gate while attempting the two-port network problems. So I think all the students have good knowledge. So we practice. So the net and the material also will be available, and this video recording is also available. You can check out the video whenever you require. So thank you for attending this class. So have a nice day. Thank you.
Thank you, sir.
Thank you, sir.